Hey guys, welcome to Pharmaease quick revision. Today we are going to study pharmaceutical analysis sem 1, the unit 1 part. So unit 1, as we can see the pic, the unit 1 part consists of two chapters, that is pharmaceutical analysis and second one is errors. In pharmaceutical analysis we are going to study its definition and scope, different techniques of analysis, your different methods of expressing concentration, primary and secondary standards, and preparation and standardization of various solutions. Okay, and in second part, that is your error, we are going to study sources of error, types of error, methods of minimizing it, and accuracy and precision. Okay, so let's start with pharmaceutical analysis. Okay, so what do we mean by the term pharmaceutical analysis? So for your simplicity, first break down the word pharmaceutical and analysis. Let's treat this two words differently. So analysis over here means to find the concentration or the strength of a given sample or a chemical. Okay, and pharmaceutical is refers to the pharmacy. So if we combine the both word, the pharmaceutical analysis, in our main aim is to find the strength and the concentration of a given sample, or concentration of a given sample which will be needing for making drug in pharmacy. Okay, so here we will be basically focusing, our main focus will be on finding concentration and strength of the given sample. Okay, now this was definition, and its scope will be like, we know that we should know that for making a dose we should know the exact amount of concentration or strength of a given sample. Okay, it is very important. So though if we don't mix them in proper concentration strength, we may not get the desired drug, right? So this is one of its scope, that by studying this we will get to know, we will finding different concentration of chemicals which will be needing for making a dose. Okay, second scope will be is of we will be finding impurities. So it will help us to find impurities, right? Of various chemicals and substance. Okay, so this was definition and scope of pharmaceutical analysis. Now let's move to different techniques of analysis. So as you can see in the screen, I've shared a flow chart. So basically the method of analysis, it is divided into two broad terms, that is instrumental and non-instrumental. And as the word is suggesting instrumental, we will be needing some of or the instrument for the technique of analysis. Okay, for knowing the strength of a sample. Okay, non-instrumental, as the word is suggesting, that we don't need any as such instrument for finding the strength of the given sample. Okay, now further, instrumental is divided into four different categories, that is electroanalytical, spectroanalytical, chromatography, and other techniques. Okay, now let's understand what are these. Now as the word suggests, electro is giving a hint that it is something related to electricity, and as I have told you earlier, that in analytical it means to find the strength. So electroanalytical will be finding the strength of a given sample with the help of electricity. Okay, now sorry, now we can see different parts of electrochemical. So all these techniques falls in this category. Okay, we are using electricity somewhere of the other in the process to find the your strength and concentration of the given sample. Okay, now it consists of electrogravimetry, conductimetry, colorimetry, potentiometry, voltimetry. Okay, now spectroanalytical. Spectro is giving us a hint of spectrum, that is your infrared and all. Okay, so spectroanalytical means we are using the spectrum somewhere or the other in the technique, okay, for finding the your strength of the given sample. Okay, this is done. There are many techniques mentioned, okay, like IR spectrography, IR your infrared I mentioned, okay, atomic absorption spectroscopy, these are all okay. Now let's move to chromatography. Chromatography is basically your color change, okay. You must have done paper chromatography in your class 12th, okay, and or you're in your college, right? So but it is not mentioned over here because it is mostly done in your school level and institution level, right? But the three things which are mentioned over here, that is GC, your gas chromatography, your HPLC, your high pressure liquid chromatography, and your TLC, that is your thin layer chromatography, and HPTLC is your high pressure thin layer chromatography. So these are the very advanced techniques and used in laboratories, research laboratories, to and they give a your very exact, very accurate results, right? These are advanced techniques and these are not used in institution level or in a school level. So that's why paper chromatography is not used. Hope you understand over here. Okay, so see guys, our this topic, method of analysis, is not that much important from our exam point of view, but we are studying this for the sake of knowledge, right? We should know that what are the different methods involved, right? So that's why we are studying. So we will not go deep into this, but we will study just for knowing it, okay. Other techniques involve RIA and your ELISA, okay. Now the second broad your part was non-instrumental. As I mentioned, we don't need any as such instrument for analyzing the compound or the sample, okay, to know their strength. So classical method, titometry and gravimetry, okay. In titometric it is mentioned that acid base, redox precipitation, non-aqueous complexometry. So titometry is like simple reaction, the chemical reaction, and the outcome of the reaction, we are that by that outcome we are finding the your strength of the given sample, okay. So these are various, we will study the, like acid base redox reaction, they are in our syllabus and we will study further in further videos, okay. So now we are done with methods of analysis. Now we will move to your methods of expressing concentration, okay. So here are five method as you can see in this screen. First is a molarity, which is represented with capital M. Second is your molality, represented with small m. Normality with capital N. Mole fraction with chi, you can say it is like this, and your formality, okay. So now let's see its their formulas. So molarity, which I mentioned, it is mentioned with capital M. So its formula is number of moles of solute by volume of solution liter, and molality, that is small m, number of moles of solute and mass of solvent. Here we have to understand one thing and keep one important thing in mind. These two formulas are similar in, but difference is this in denominator, that is in molality it is volume of solution, and in molality mass of solvent. Now I hope guys you know the difference between solute and solvent. If in case you don't know, I'm here to help you out. So let's say it's a beaker and they are water, and you put some sugar, your particles, okay. So the thing which is present in large quantity is your solvent, right? The thing which is present in large quantity or large volume is a solvent, and the thing which are present in your small quantity is your solute, right? So here water will be solvent and your sugar particle will be solute. So we are done with the two formulas, that is of molarity and molality. Now let's move to normality. As you can see, its formula is number of gram equivalent of solute by volume of solution. Now how we will able to find the number of grams equivalent of solute? So its formula is mentioned over here, that is your, we have to multiply the weight of solute with its equivalent weight of solution, equivalent weight. Okay, we have to, for finding number of gram equivalents of solute, we have to multiply its weight with its equivalent weight. Now how to find equivalent weight? The formula for equivalent weight is molecular weight by basicity in case of acid, and acidity in case of base. Okay, now what is these terms, acidity and basicity? Okay, let's take an example. Let's take HCl. Okay, HCl, we all know that this is an acid. For acid we find basicity. Okay, so basicity is nothing, just keep in mind that it is how much hydrogen ion it will liberate in aqueous medium, right? How much? So here we all know that HCl will liberate only one hydrogen ion in your aqueous medium, so its basicity will leave one. Simple. Now takes let's take another example of any base. uh, what's not happening here? Okay, uh, NaOH, right? We all know this is a base. Okay, we'll find its acidity. So we all know that it will release only one OH. Okay, one OH ion in aqueous medium, so its acidity will be 1. Simple. Okay, so we are done with molarity, molality, normality. Okay, the fourth is mole fraction. Let's suppose we have a beaker, and I have dissolved many particles like A, B, C, D, right? E, many. Okay, now if I have to find the fraction of A present in the solution, that is mole fraction of A, then it's simply like you guys have calculated mean earlier in mathematics topic, right? So it's like that only. So for finding the mole fraction of A, it's like mole of A by total, like there are uh, four thing present, like A, B, C, D. So it will be like mole of A, mole of V, mole of C plus mole of D, right? If E is also there, then mole of E. So the thing which we have to the thing which we have to find by total, there's sum. Okay, and how to find the mole of A? The formula for this is given mass by molar mass. Okay, given mass by molar mass. Okay, now formality. You have now one thing you should keep in mind, that your main focus should be in molarity. Okay, and your mole fraction, because they are widely used. Normality and formality are not that widely used, but as I always say, you should know that for the sake of knowledge. Okay, let's see the formula of formality. The formula of formality is number of gram formula masses of solute by volume of solution. And we have an another formula, it's like a mass of ionic solute, that is we are the ionic solute, that is we are like NaCl and all. Okay, the mass we are dissolving in the solvent, okay, in grams, in ionic form. Okay, by gram formula mass of solute into its volume of solution in liters. Okay, now we done with the different expression of methods of expressing concentration. Okay, we are done with the 5. Okay, now let's move to primary and secondary standards. Primary standards. Now primary standards are those which concentration is known and they are of very high quality. They are of very high purity. Okay, the concentration is known and they are of high purity. Okay, there are some properties of your Tryman standards. They are like it should be highly stable. Okay, it should have high molecular weight. Okay, it should be obtained in pure state. As I mentioned, it is highly pure, so it should be obtained in pure state. And it should be of high solubility. High solubility refers to readily soluble in water. How much it is readily soluble, how much it is easily soluble. Readily over here means easily, how much it is easily soluble in water. Okay, now let's move to secondary standards. So secondary standards are those solutions which are of which are not of high purity. Okay, and we don't know their concentration. We have to, if we have to find the concentration, we have to standardize it with the help of primary standards to know its concentration, right? So primary standards are those which are of high purity and concentration is known, and your secondary standards are those which are not high pure, and we have to standardize it with the help of primary standards to know its concentration. Okay, so before we move further, we should know two terms. Okay, I've seen many guys getting confused in these two words. So these two words, as you can see in your screen, that is titrant and titrate. So how to remember this? These are very similar like words like titrate and titrant, right? So how to remember? So there's an I'm giving a trick, you can use it to remember. So to remember this, you can simply say that CR7. Now I don't have to introduce you that who are CR7. Okay, uh, so CR7 is C here represent the conical flux. Okay, C here represent the conical flux, R represent the rate. Remember, rate, RATE, the last word I am focusing on, rate. Okay, 7 is your rupees price. So rate of conical flux is rupees 7. Okay, CR7. So if you are getting an idea that the rate titrate is in the solution in conical flux, then titrant will be the solution in burette. Hope the doubt clears in your mind. Okay, so now let's move to the preparation and standardization within solutions. So first is oxalic acid. Its formula is COH ka whole twice. Okay, so as you can see, since it is a primary standard, as I mentioned, it is of non concentration, right? So there is no need to standardize it. Okay, so how to make it? Its preparation is like weight 6.3 mg and dissolve in 1000 ml of distilled water, right? Okay, we don't have to standardize it, it is the easiest of the all. So let's move to the second one, potassium permanganate, that is KMnO4. Okay, so the question will arrive in your question write the preparation and standardization of KMnO4 or potassium permanganate, right? So you have to mention over there that principle, then a chemical reaction, then a preparation. Then here I have not mentioned one thing, but you have to mention in your exam, that is where I am underlining here, after the preparation step, your procedure, right? Then you have to do this diagram, your purity diagram. Okay, so procedure is I have not mentioned because it's the same for the all, like you have to wash the burette, you have to wash the conical flux apparatus and all, you have to rinse the burette, and basically you have to write all the step the preparation step and the sanitary step in sentence form, right? So that's why I have not mentioned that. I know you will guys will mention it. Okay, so preparation, let's see its principle. So KMnO4 acts as a oxidizing agent in acidic medium that oxidizes oxalic acid into CO2, right? Let's see the for chemical reaction, that is KMnO4 plus C2H2O4, that is your oxalic acid, plus H2SO4 that I mentioned here in acidic medium, that's why we are using H2SO4. So it is giving us K2SO4 plus KMnO4 plus your H2SO4. Okay, so preparation, So we will wait about 3.2 KMnO4 and dissolve it 1000 ml of C. This this is a weight, right? Like like your over here 3.2, earlier it was your 6.3 in oxalic acid, here it will 8.5. So this thing we have to memorize. Okay, one thing we don't have to memorize it, all the thing will be dissolved in 1000 ml. Okay, so no need to worry about those. We just have to uh, uh, memorize these things, that is 3.2, 8.5, 6.3, right? So okay, now let's see the standardization of KMnO4, how it is done. So KMnO4, so uh, as I mentioned you that KMnO4 is present in burette, so it will be your titrant or titrate. CR7 remembering, so it will be your titrant. Okay, titrant. Titrate will be your all the things present in your uh, conical flux rate. Titrate. Okay, so KMnO4 here will be titrant. Okay, now in conical flux we will take 20 ml of oxalic acid. Okay, so you don't have to see this was done for understanding better. This nothing, this is written by mistake only. So in conical flux you have to take 20 ml of oxalic acid plus 5 ml of H2SO4 for acidic medium plus indicator. Indicator we are using is phenopthelene. Okay, now initially the color will be colorless. Okay, on adding the KMnO4, when we will observe pink color, it will be our endpoint. So we can say we will be get our endpoint when we will see a pink color will be observed in the conical flux. So endpoint will be colorless to pink, right? So this was the standardization of KMnO4. Now let's move to HCl. Its principle is HCl reacts with known strength of Na2CO3. The known strength they are using means it is primary standard over here. Okay, so chemical reaction is as follows: Na2CO3 plus HCl gives 2NaCl plus H2O plus CO3. Okay, now this you have to remember yourself. Okay, weight. Weight 8.5 HCl and diluted with 100 ml distillate. DW is over distilled here. Okay, I've wrote them in short. Okay, now how to standardize? Take the HCl in burette, that is titrant, and titrate will be your this is like this. Okay, don't forget this. Anhydrous Na2CO3, your 0.3 gram. We have to take 0.3 gram of anhydrous Na2CO3. Anhydrous means absence of H2O, that's why it is mentioned over here, plus 20 ml of distilled water. So we have to dissolve 0.3 gram of Na2CO3 in 20 ml of distilled water. Then we have to mix 2 drop of indicator. We can use either methyl orange or methyl red. It's up to us, it's our choice. Okay, so end point will be observed from initially it will be colorless, and on initially it will be of different color, but on adding HCl to the solution we will be observing pink color, so thus our endpoint will be observed. Okay, now we will move to preparation standardization sodium thiosulfate. Guys, preparation standardization sodium thiosulfate and your KMnO4 are two most important thing. Okay, they are repeatedly asked in the questions. So though HCl is important but not that much, you should focus more on KMnO4 and your sodium thiosulfate. Okay, the formula for sodium thiosulfate is Na2H2O3.5H2. Okay, so its principle is like when potassium iodate reacts with Ki gives I2, which in acidic condition, then this I2 further reacts with your sodium thiosulfate. Okay, let's see the your reaction. KiO3 plus Ki plus H2SO4 for providing acid condition gives us K2SO4 plus I3 plus H2O. This I2
is this I2 is further reacting with sodium thiosulphate and giving us sodium tetrathionate. If you are facing difficulty in memorizing long words like thiosulfonate, tetrathionate, okay, so break down those words into small piles, like small parts like I have done here, like tetrathionate, sodium tetrathionate. So it will be easier for you to memorize those things. Okay, so it will form sodium tetrathionate and sodium iodide. Okay, so we have to wait. Now its preparation, we have to wait 24.8 gram of sodium thiocyanate and dissolve in 200 ml of freshly boiled and cooled water. Then we have to make it to the volume of 1000 ml by adding 800 ml of distilled water. We are doing this because first we are dissolving 200 ml, then 800, because to dissolve it properly. Okay, so let's see this standardization. Okay. So in burette we will take sodium thiosulfonate, and in your conical flux we will take 10 ml of KiO3 plus 2 gram of Ki plus 5 ml of dilute H2SO4. Then we will be add 2-3 drops of starch indicator over here is starch. Okay, so as I mentioned that when KiO3, Ki and H2SO4 reacts, they release I2, and when I2 and starch release, they gives a blue color. Okay, so initially we get an idea that initially in conical flux it will have blue color. Okay, so will we we will be observing an endpoint when blue color fades away by adding sodium thiosulfonate, and the solution will become colorless. So endpoint will be observed from blue color to colorless. Okay, on adding your titrant, that is your sodium thiosulfonate. Okay, now with this we are done with the your pharmaceutical analysis part. Now let's move to the errors part. Okay, now what do we mean by the term error? Okay, so let's say uh, this is a road. Okay, this is a road and its total length is of 100 kilometer. Okay, 100 kilometer, and we have given a task to measure it. We have measured it of 99 kilometer. Okay, now this 100 kilometer will be a true value because the road is of that length only. Okay, and your 99 kilometer is your measured value. Okay, so uh, so the error is simply the difference between the measured and the true value, right? Okay, so there are two ways to obtain true value. First is absolute method. In this we use known quantities, okay, in sample. Okay, primary standards, like to minimize the error. Okay, and in second it is comparative method. In this, if we are not for any case, if we are not able to perform the experiment, so we will take the relevant data from a relevant source, like your pharmacopoeias and all, right? So these are two techniques which are used to find the true value to minimize the error. Okay, now sources of error. So first source is of human source, as the word is suggesting uh, human, it is related to mistakes done by the human. Okay, so it's all these things like misinterpretation of the your readings, like readings is coming 72.4, but you are noting it down 74.2, so it's your mistake, right? So it is basically the mistakes done by the experimenter, human error, human source. Okay, instrumental and apparatus, they may not be well calibrated. Okay, what is the meaning of calibration? Okay, let's see. Now suppose this is a beaker, and 100 ml is here, 50 ml is here. Okay, but due to some reason the printing mistake does an error, and it marks 100 over here and 50 over here, or vice versa, upper or down. Okay, not in the correct position, right? So when the markings are not at the correct position. Okay, so they are not termed as well calibrated. Not only markings, you can say your diameter of the your test tube and all. When it is not up to the mark, it is not up to the your required your dimensions, it is termed as not well calibrated. So uh, as you can see, if the instrument is not well calibrated, we will be not measuring accurate amount of solutions, and it will be hamper our reactions. Okay, so it will be act as a source of, they should be well calibrated, right? Third is experimental condition. Condition refers to your some products or some reaction are highly sensitive to pH, some are sensitive to your temperature and all, right? So we need to maintain that ideal condition. So it's all depend on the and experimental condition we are performing the experiment, right? Sorry. Sorry. The fourth is constituent used in analysis. See, the more will be the pure substance we will be using in our experiment, the chances of less error will be there. Okay, the more impure, the more impurities, substance with impurities we use in our analysis technique, the more chances of error will be there. Okay, so this was in this. And fifth year is procedure. Like there are two ways of performing our experiment. It is A and B. In A, we know that it is 90% chance of getting a false result, and in B it is 10% chance of getting a false result, your incorrect value. So which method is good? Obviously of method B. Okay, so procedure. Okay, if we method or procedure, if we are not following the procedure, right, and like we are skipping some steps in the experiment, we are not following the procedure which need to be followed, so it can act as a source of impurity, right? So now let's move to the types of errors. uh, uh, Types of error. So there are basically three types of errors. That first is your symmetric. I have mentioned it A. Symmetric error, also known as non-random, or uh, your determinant error. B is your random indeterminate error. Three is your gross error. Okay, so symmetric error is the source of error is known and they can be minimized. Obviously, if the source is known, we can work on it and can minimize it. Okay, random error is, as the name suggests, sources are not known and they cannot be eliminated. Imagine you are doing an experiment, you have provided all the ideal conditions, you are all fully satisfying all the thing, but still there you're finding some amount of error. So but you don't know the source, how it appears. Okay, nobody knows, right? So these types of errors comes in this. Since the source is not known, so we will be not able to eliminate, right? Third is gross error. It is done by the uncarelessness of the experimenter, right? Like he is not like the bureau reading is 50, his reading is 49. So it is not the fault of the instrument, it is fault of the your experimenter, right? If he noted the amount 50 but noted down in his copy, right, 51, so again it is his fault, right? So these are the types of error. Now is your A part. These five are the of symmetric. So these are like same, only that personal error, that is your human error, instrumental error, as I've mentioned over your here source of error. It's like same, only you have to just wordings are change. Okay, it's wording and change. So if the instrument is not calibrated it to minimize the error. If you have done any mistake, that is human error, minimize it, don't repeat that mistake, it will minimize the error. Okay, so this was, if you have not followed the proper procedure, follow it, it will minimize the error. So this was like, okay. Now, methods of minimizing error. First method is of proper calibration of apparatus and instrument. Okay, if you properly calibrated the instrument, if you use, the chances of error will be minimum. Okay. Second was by running control determination parallel to the sample by taking standards. Okay, let's see. In this, you will be performing an experiment with your test sample, and parallelly with same method you will be doing it with a standard are okay, for reference. Okay, so this imagine you are getting by a test sample a value of 5, and in your video your standard your 5.5, so difference is 0.5. so you can take the difference and you can predict the minimum value close to the true value, right? So this was third is by running blank determination to know the effect of impurities. So in this we will it's like control determination only, but it is just to know the effects of impurities introduced by the reagent in the process, right? Fourth one is by comparing result of independent. So performing the same, like if we have to like I've given an example, if we have to know the strength of HCl, so we will be follow two methods, method A, method B. Okay, in like in method A we are getting a value of 10, and in method B we are getting a value of 11, so difference is 1, so we will predict that it will 0.5, so it will be 10.5, so it will be close to the true value, right? So will be like this only. Fourth is by using standard addition, we will be adding standardized to our reagents. Okay, and sixth one is by using your internal standards, we will be using standards as our reagents. Okay, and now accuracy. As we know that accuracy is inversely proportional to the error, as you can see in the box. Okay, so the more will be accuracy, the less will be error, the less will be the accuracy, the more will be the error. Okay, so accuracy can be defined as uh, how much close the measured value is to the true value. Like the true value, let's say, is your 5, and our measured value is 0.9. It is approximately close. Okay, 0.1 is difference. Okay, so how much it is for one time, and precision is your degree of closeness by several measurement of same quantity and same type of same method, right? Accuracy is for one time, that how much closer, and precision is for several method for the same thing for by the same method, right? If let's see, first time we get 0.9, second time we get 0.8, third time we get 1.1, fourth time we get 1.2, it's like this. Okay, we will take the mean out of their difference and we will add and divide by 2, divide by 4. Okay, we will get a true value, right? The precision is your degree of closeness between several measurement of same quality of sample and same method. It should be very important for following same method and your quality of sample. Okay, and your accuracy is degree of closeness, the how much it is close to the true value, right? And here you can see types of precision. You just have to give it a read and you will be all done. So that's all. We have finished with the unit 1 of pharmaceutical analysis, and thank you for listening us. If you like the video, please like it, share it, and subscribe it. And thank you for listening me. Thank you very much.